Hi everybody and welcome to the 11th video in the series TensorFlow Basics with Hemant, and that's myself. In the last couple of videos we have been talking about the Keras layers. So different layers we discussed. We discussed core layers, then we discussed layers which are related to solving the sequential problems. In the last video we talked about the convolutional layers. So we have pretty much covered what are the different layers which are offered by the Keras. But when it comes to the training of the Keras model, there are a few things which are required on top of the layers. So one of them is loss function, second is optimizers, and going forward we also need to tune the hyper parameters of the model, right, that we have trained. So these three things are the topic of this 11th video in the series. So we'll be talking about why do we need loss functions and what is the purpose of the loss function, and then what are the typical loss functions for the binary and the multi-class classification, what loss functions are used for regression, what are optimizers, and what are the common ways, common types of the optimizers. And then finally we'll also take a look at how do we tune a model. So that means how do we find the right hyperparameters of the model. Okay, so let's get started, guys, with the loss functions. So loss function basically estimates how closely the distribution of the predictions made by a model matches the distribution of the target variables in the training data, right? So if you look at this particular picture here, what you'll see that this is the softmax output of the model. So usually what we do is the model will calculate the logits, and then we apply the softmax function to get the probabilities. And then we typically for the binary or for multi-class classification we use the concept of a cross entropy loss. So in the cross entropy loss, what's going to happen is we are going to compare the softmax values, that is the predicted values, and the labels, and then we are going to be using a function which is called as a log loss, and then this particular loss is calculated, and then based on this loss the optimizer is going to calculate the gradients, and then based on those gradients and couple of other things, depending on the type of the optimizer that we are going to use, it is going to adjust the weights, right? And what is the purpose of doing all this adjusting the weights is basically it's to minimize the loss, right? So we want basically the predicted value to be more or less similar to the target values or the target labels if you are talking the classification problems, right? And one of the characteristics of the log loss is when when the predicted probability of the true label is close to the true label, then the loss is less, and if the predicted probability for the true label is less, then the loss is going to increase exponentially, right? So in this particular slide, just keep one thing in mind, that we are trying to match the predicted value and the expected value. So expected value in case of regression, it will be a number. In case of classification problem, it will be some kind of a label, right? So we compare those two things. So the purpose of the loss function is to calculate the difference between the actual value and the predicted value, and the function of the optimizers is going to be taking this value and then calculating the gradients and adjusting the weights of the model, so that in the next step hopefully the loss is going to be less than what it was in the earlier step. Okay, now let's try to take a look at what are the different loss functions used for the binary classification, right? So one of that is binary cross entropy. Okay, so binary cross entropy, when we are using when we have a classification problem which is a binary classification problems, that means we have two classes and we are trying to predict one of those classes, then we use the binary cross entropy. Okay, so what about this cross entropy? Cross entropy, as we saw earlier, actually it is this is the way of calculating the difference between the labels and the softmax outputs from the model. Okay, so entropy is basically a measure of uncertainty. Okay, so lesser the uncertainty, lesser the entropy. Okay, and that is the purpose that we are having. Actually, we want to minimize this cross entropy because we want the predicted distribution very similar to the actual distribution of the labels, right? Now there is another variation which is categorical cross entropy, and that is used for the purpose of classifying the multi-class problems, right? So say for example different kind of animals, right? So number of like types of animals will have more than two labels. So in that particular case we have multi-class classification problem and we use categorical cross entropy loss. Okay, now in Keras, when we are using the categorical cross entropy loss, it is expected that the labels are one hot encoded, right? Now sparse cross entropy loss is also similar to cross entropy, and it is also used for multi-class classification. The only difference is in the sparse cross entropy loss, we do not need to one hot encode the target variables or the labels actually. And then there are a couple of other variations of the loss functions also, which is like callback, Libra divergence loss, and for the SVM purposes we also use the Hink loss. Okay. Now, how does the loss function and the output layers relate? So for the regression problems, we have this output layer configuration. Output layer will be one node with a linear activation unit because it's a regression problem, right? And the loss that will be using the mean squared error. Binary classification problem, we will be using the sigmoid activation unit, and the loss function will be either binary or categorical cross entropy. And for the for the binary it will be binary cross entropy, and for the multi-class classification it will be either the categorical cross entropy or the sparse cross entropy, sparse categorical cross entropy. And in the case of multi-class we will be using the softmax activation function also, right? Now let's also take a quick look at the regression loss functions. So there are three variations here. One is the mean squared error. So we take the difference between the predicted and the actual and then square it. Now there is another variation which is mean squared logarithmic loss. So what happens is, in case of mean squared error, if the difference between the predicted and the actual is quite high, then if you square it actually, that value, it will have a lot of impact on the difference if we square it. So if we do not want that, that means in which if the target value has a spread of values, that means some of the values are really far away from the actual values, then it might be useful to use the mean squared logarithmic loss, right? So it will be higher but not as much as the squared error loss. And then we also have the concept of a mean absolute error loss. So uh, so for example, if you have outliers, then it might be good to have mean absolute error loss. Okay, large or small values, so you want to basically average out the errors in both the directions. Okay. Now coming to the optimizers, so in the optimizers, actually gradient descent is the most kind of a basic optimizer that we have. And then what happens is actually we have a target function, and we take the derivative or the gradient of that particular function. And then what we do is we take the derivative and multiply it by the learning rate over here, and then subtract it from the actual weight. So we are trying to update the weight, so we take this gradient and then we multiply it by the learning loss, and then we subtract it from the weight, that is a previous weight, and then we get a new weight, okay, for a particular parameter, right? So this is how we keep on adjusting, and then we reach the minima, okay, of that particular function. So here we are changing the weight, and accordingly the loss is also changing. So in this particular case we are decreasing the weight, and as you can see, it is moving towards the minima. Right now, once we pass this minima, then once again the loss will start increasing, and then you'll have to keep on tuning in the other direction. That means you will have to increase the weights to come to this particular point. Okay, so the purpose of the optimizer, as we were discussing earlier, is basically to take the loss and then update the weights based on this formula, and then hopefully we'll reach a value of the weights which will give us the minimum loss. Okay, now this is the most basic algorithm, and the kind of the hyperparameter is learning rate into this particular case. Now learning rate, if we keep the learning rate too high, then model will converge faster. But then if the step size is too high, it might just miss this particular point and once again go somewhere here, and then it'll kind of oscillate if the learning rate is too high. And if the learning rate is too small, then obviously since we are making very small updates here, it is going to move very slow, and it will take more amount of time. Okay, now the learning rate basically must be discovered via trial and error. So we have to try different values of the learning rate, and then we have to see how the model is going to perform, because see, configuration of the network and the data, they are going to have an impact on how the model is going to converge. So for each model that you have and the data that you have, you'll have to try out the different learning rates. Okay, now that is the only option that we have with the gradient descent. Okay, now there is another parameter which is associated with the plain vanilla gradient descents, and that is momentum. Now in the momentum, when we consider the momentum, which is exponentially weighted average of the prior updates to the weight. That means so for example over here, let's say one particular calculation tells us that go in this particular direction, but if the momentum tells us that okay, we need to kind of increase the weight, then we are going to give certain importance to the momentum also. So we'll listen to the momentum. So like last 15 readings have been saying that go in this direction, and the last calculation told us that go in this direction, then we will probably reduce the amount of the calculation will be done in such a manner that the weight will not be reduced drastically, because the last 10-15 readings have been saying that go in this particular direction rather than going in this direction. Okay, so that is the concept of the momentum. Momentum means we are basically going to use the exponentially weighted average of the prior updates in addition to the learning rate actually. And we will see the kind of the impact that has when we go to the uh, notebooks. So momentum is going to add the inertia to the update procedure, so it's going to be kind of resistant to the changes suggested just by the last calculation that we do on the gradient. Okay, now what if we wanted to kind of change the learning rate as we train the models? So there is a concept of learning rate schedules. So there are ways to automatically change that learning rate as per the schedule. So we can decay the learning rate as we step through the epochs of the model. So that's one way. Okay, the second way is actually we can also use some of these optimizers, AdaGrad, RMS prop, and the Adam, which basically are adaptive learning rates. That means we don't have to tell like what should be the learning rate. The algorithm is going to figure out the learning rate for themselves, right? Uh, some other kind of comparisons about the different algorithms. So these are kind of positives, and these are the negatives about those algorithms. So gradient descent essentially, as we saw, it has got a learning rate, right? We use a learning rate in the gradient descent, but the learning rate is same for all the features or the parameters. Parameters, all the weights, the learning rate is the same. So uh, for example, if you have three different type of weights in the model, all the weights are going to be updated based on the same learning rate, right? And another thing is, if we do not have the momentum configured, then it is also likely to get stuck in the local minima, right? And momentum can help in this particular case, like if we really want to come out of the local minima and uh, go towards the global minima, if it exists, then momentum can help, because it will push through the local minima and help you to get to the global minima. Okay, now in order to get over some of the kind of disadvantages of the gradient descent, the AdaGrad was kind of invented, and here we have parameter specific learning rate. So each parameter is going to have its own learning rate, and that is going to get adjusted based on all the pass gradients. Okay, now problem with the AdaGrad is that it can slow the search down too much, because it depends on all the past gradients. Now in order to kind of improve over this RMS prop algorithm basically started using the decaying moving average of the gradients to fix the problem of the AdaGrad. So essentially RMS props is going to pay more importance to the updates which are made in the recent past, rather than considering all the readings of the past. So like the readings which are too far, they will have lesser importance, and the readings or the gradient updates which are made recently, they will have more focus, okay, for the calculation of the new weights. Okay, now ADA delta is once again a further extension of RMS prop, and it basically improves the process of learning. It basically improves the speed of learning uh, the parameters of the model quickly. And Adam is the the most popular one, and Adam is probably a good starting point for most of the problems. So it uses exponentially decaying mean gradient, that is the first moment, and the variance, the second moment of the weights for each input variable. Okay, so that's the comparison of the different optimizers that we might have. So we spoke about the loss functions. This is kind of the summary of the different optimizers also. Now let's have a look at the tuner library also. So Keras Tuner library will help us to pick the optimal set of hyperparameters. So what are the hyperparameters? Hyperparameters are variables that govern the training process and the topology of the machine learning model. And most important thing, they are going to remain constant over a training process. That means once we select the hyperparameters, they are not going to change unless the training is completed. And then there are two type of hyperparameters. One is the model hyperparameter, and the second one is the algorithm hyperparameters. So model hyperparameters, like the width of the hidden layers, the number of the hidden layers and all, they are the model hyperparameters. They basically influence the structure of the model. And then the algorithm hyperparameters, something like learning rate, okay, they are basically impacting the configuration of the algorithm, right? So two different kind of algorithms that we have. Okay, now as far as the Keras tuner goes, the way that it finds the right set of hyperparameters, so there are four different kind of ways which are available. So one of them is the random search. So random search is the least efficient approach, and it's going to search pick the values of the hyperparameters randomly and going to try and see if that is good or bad, like whether we are getting better result or the same kind of results or even the worse results than our last trial that we had. Now it does not consider the previous trials. Okay, so say for example we tried combination 1, then that combination 1 will have no impact on the next kind of a random search. Now Bayesian optimization, whatever trials we do on the hyperparameters earlier, they are going to be considered for choosing the hyperparameters in the subsequent trials. Okay, so Bayesian is kind of smarter because it is going to learn from whatever trials that were done prior to the current one. And then the hyperband, what is going to happen is in the hyperband, say for example we started with 20 different models. It's going to try out for few epochs and then it's going to throw out, say for example 10 models out of 20, and then it'll take those 10 the best models, and then it'll try to reduce it to 5 and things like that, right? So that is the concept of the hyperband parameter tuning. And then there is also the scale learn tuner, which is offered by Keras, which is to be used with the scikit-learn models. Okay, now before we come to the summary, let's skip through the step through the the notebooks that we have. So this is the first notebook that I have open for us. Let me zoom it a little bit. Okay, now what we are going to do is we'll see how to use the loss functions. So the first problem that we have is basically a binary classification problem here. So we have two sets of points here. One is the orange kind of points, another is a blue points, and we want to classify. Now say for example if we are given this point, we have to predict its label, whether it is blue or orange, right? So cross entropy, so this is basically a binary classification problem, right? So there are two classes and we have to classify between the two. So let's generate this particular data set quickly. kind of slow. Okay, okay, we got our data. Now next thing what we are doing to do is we are going to create a model here, right? So model, it has got a dense layer, another dense layer, SGD, and what we are going to be doing is we are using this activation ReLU, and the output is sigmoid. So we saw that, right? For the binary classification we use activation, sigmoid activation, and we have defined the learning rate, we have given some weight value to it, and momentum we have given some value. And then while compiling the model, we select this binary cross entropy here, and the optimizer as a SGD, stochastic gradient descent. And then we basically are going to see the results for the loss and the accuracy. So let's quickly go through this. Let us started. There we go. So we got a training accuracy of 0.832, test of 846. So these are the graphs actually. So this is the graph of the loss, and this is the graph of the accuracy. So validation is in fact slightly higher than the training in this particular case, right? So very simple. When we compile the model, we use this loss equal to binary cross entropy, and the activation in the model was set to sigmoid, and we had configured this learning rate and a momentum in this particular case. Okay, now let's do a multi-class classification. We have three sets of point here. So let's generate this particular data. That was quick. And what we are going to do here is we are going to be once again using a sequential model, and the activation is softmax because it's a multi-class classification, right? So we have three classes in this particular case, and we are going to be using the loss function is categorical cross entropy. Okay, now if we have the categorical cross entropy, we also need to hot encode the labels. So this is what we are doing here. Actually, we are using this Keras utility to hot encode the models. Okay, and let's see how does this go through. There you go. So these are the results that we get over here. Now we can also try one more thing here. So rather than using the categorical cross entropy, let's change it to, so let's say we do not hot encode the labels. Okay, what will happen? So let's just try to comment this and try to run this, and we should get some kind of so we are getting an error here. Okay, because we need hot encoded labels over here. Now as we said, if we use a sparse categorical entropy, we should be. So as you can see, the impact of the different learning rates. So for a very high learning rate, it is not able to stabilize the training. Now the learning rate of 0.1, it seems way better, and then this is kind of very small. These are the small learning rates, and as you can see, uh, the the graphs are not very useful, especially these ones. They are not very useful. So this seems to be the probably kind of the best learning rate. Okay, so it's very simple. You just have to plug in the, we have to try the different learning rates, and then see which one is working for the model configuration that we have. Similarly, we can also try the different momentums also. So here what we are doing is we are giving the momentum also, and we are feeding these different values of the momentums here. So these are the results for the different momentum values that we have, right? So these two values like zero point 0.9 and 0.99, they seem to be working the best actually, as you can see. Then we can I have also tried these different adaptive methods, so stochastic gradient descent, RMS probe, adagrad, and adam, and these are the results as you can see. So as you can see, with the plain vanilla stochastic gradient descent, it's it's not stable pattern of learning. Model is not able to learn, and with the RMS prop, it is kind of converging. Adagrad is also okay, and Adam seems to be the best out of all the adaptive learning methods that we have. So what has been done here in the adaptive in this particular thing is, when we create the optimizer, we are saying optimizer equal to optimizer, and we are passing all these different values for it actually. Okay, so I'm just trying to see where is that line where, so we are passing the optimizer, the value of the optimizer here, and when we call this fit model, we are passing this particular value here, adaptive I. So one of these methods is going to be passed, so that is where you see all these different graphs for the different optimizers. Okay, so SGD, plain SGD is not good enough in this particular case, and with the adaptive methods, so Adam appears to be the best in this particular case. Okay, now let's turn our attention to the hyperparameters. So as we discussed earlier, there are two different kind of hyper parameters. One is a model hyperparameter, then there are algorithm hyperparameters, and hyperparameters do not change throughout the process of the training, right? So there is a library which is called as Keras Tuner that we have to install. So we installed the Keras Tuner, and once we install, we can also get a minced data set for as a data, so that we can try the hyperparameter tuning model. So there are two different ways to build to define the hyper model. One is to do the model builder functions, and that's what we are going to do. But there is also another way of doing this, which is subclassing the hypermodel class. Okay, but we are not doing the subclassing approach here. So we are defining a function which is model builder. So in the model builder, what we do is we define certain hyperparameters. So the number of units, it is like we want to try the different integer values starting from 32 to 128 in the steps of 32. So this is an integer kind of an hyperparameter, and in the layer that we are going to define here, we are going to use this HP units here, right? So outside when the hyperparameter steps through, it's going to change this value, and the dense layer will have a different number of neurons, right? Similarly, we are going to also define another one, which is HP learning rate, and which is hyperparameter dot choice, and these are the two different values. So we are going to try, and then what we do, we choose the optimizer loss metrics, and then we say learning rate we are going to pick up from this one. Okay, so let's define this function and then we instantiate, right? So you remember there are four different kind of tuners which are available in the Keras tuner. So one of them is hyperband, so we are using the hyperband here and we are passing this model builder over here, and then we are basically trying to optimize the hyperparameters using this objective. Maximum epochs is 3 and a couple of other parameters we have. Okay, that's done. This is the just a callback to clear the output between the epochs. So that's done, and this is how we are going to search for the right hyper parameters. So tuner dot search. So tuner is created here, hyperband type, and then we are going to call a search method on it. So we are going to give the data as our model dot fit. We are going to define the validation data and the callbacks, and then we are just going to search through this. So it'll start the search of the hyperparameters. So it basically came out saying 128 of the. It gave us these two different values of the hyperparameters, and then what we can do is we can basically create a model with those best HPS hyperparameters that we got here, and we can just fit that model with the data that we have, as simple as that, so that it is ready for the prediction. So fairly straightforward. We just have to create this model builder function in which we define the range of the different hyperparameters that we want to try. We also configure the different layers of the model, and then we instantiate that particular the tuner using this model builder function that we have, and then we can search for the right hyperparameters using the tuner.search. And once we get our best hyperparameters, we can use them to uh, set our model to use those best hyperparameters. So what we do is we set the hyperparameter models into the model, and then we fit it on the data, because we saw that the hyperparameters are basically constant till the training is done. So we do the training after that with the best hyperparameters, and then we can check the results, like what kind of accuracy and the losses we are getting. And it is also going to be saved into the specified directory, so that you can go and take a look at the data for all the trials which happened while the tuning of the model happened actually, right? So that is pretty much I had for this particular session. Let's summarize very quickly. So what we discussed the loss functions. So for the classification problems, we had binary cross entropy, and then we talked about categorical cross entropy for multiclass. We also talked about the sparse categorical cross entropy. Then we talked about different optimizers, so including stochastic gradient descent, the ADAGRAD, RMS prop, ADAM, all these different optimizers, and with the HGD we can use the learning rate schedules We can change the learning rate, we can change the momentum with the HGD, and see what is working best for a given problem. And then we talked about the Keras Tuner API also, so it will search for the best hyperparameters for our model, and once it has searched for those best parameters, so we can use those best parameter to fit the data and basically get the predictions from the model, right? So that was pretty much the summary of this particular session. I hope you enjoyed the video and learned something new out of it, and thank you so much once again for listening to the video, and I shall be back with a new video very soon. Thank you so much.